Okay, good morning. We'll start. I think everything works, hopefully. So welcome. So this is the first lecture of deep learning. So we have quite a few things to talk about today. I will start first with an introduction about deep learning, just to motivate everything we can do and basically to describe you what's the state of the art in 2025 in deep learning. And then after that, I will tell you about how the course is organized. And finally, during the second half of this morning, we'll have the first lecture where we'll go over we'll do a recap on statistical learning theory, so what you should have learned in intro to machine learning. So we'll go very quickly on that. Okay? All right. So the outline for today, so I will tell you about the various lectures we'll have together. Then I will give you this introduction to deep learning, and then we'll go over the fundamentals of machine learning. So the course for this year will be divided into 12 lectures, one every week. So the plan for this year goes as follows. So we'll have a first trunk of 4 lectures where I will basically teach you the basics of deep learning. So we'll have first today a recap on the fundamentals of machine learning, as I said already. And then we'll have 3 following lectures, one on multi-layer perceptron, which is like the basic architecture of a neural network, which is like the model we'll keep using and improving during this course. Then we'll have a lecture on automatic differentiation, which is a way basically to differentiate any any program, including neural networks, which will be necessary to train them, so to optimize the parameters of these models. And finally, we'll have a lecture on optimization algorithms that you can use to train these models. Okay? Together with these 4 lectures, you will have 2 homeworks to teach you the basics about PyTorch, so that you can then get started when you will have to implement a more complicated model in your project. Okay? Then in the second part of the course, we'll have 8 more lectures. On the left, you see there will be 2 lectures on first convolutional neural networks and then computer vision. So basically neural network that you can use to process images or videos. And you will see that in order to make this efficient, you need to adapt the architecture that we would have seen previously. Then we'll have 3 lectures on neural network that you can use on data which is not tabular nor image-like. By that I mean if you have sequences like text, or if you have graphs, things like this, you also have architecture that you can use on this kind of data. And so these 3 lectures are quite important. I'm not saying the others are not important, but these ones are a bit more important than the others because they are really driving everything that you see today in the news. So the attention mechanisms that we'll see, they are the mechanisms that are used to implement transformers, and transformers are the architectures that, for example, are driving models like ChatGPTs and other kind of interface. In lecture 8, what we'll do together is that we'll actually implement a small GPT model. So starting from 0, we'll open a notebook, and then we'll implement everything from scratch up to a complete transformer model, which we'll also train during class. And you will see that in one morning, we can implement something which is able to recreate Harry Potter. Okay? Then, finally, we'll have 3 final lectures on generative models. We'll have one which is dedicated to estimating uncertainties with neural networks, where we'll see architectures like mixture density networks, normalizing flows, and others. And then finally, we'll have 2 more lectures, one on variational autoencoders, and the last one on diffusion models. Diffusion models are the kind of architecture that you see, for example, to create images. So we'll see how to do that. And we will also see that these models we can also actually use them to do things that are more interesting than just generating cats. There are plenty of other applications of these models. Okay, so that's the plan for this year. There is no change from last year. The content is really the same. Voilà. You also see that there is a project associated at the bottom that you see on the slide. So what you will have to do, but I will detail that later, is that you will have a project to do by yourself, I mean, in a group, but you will have to basically decide what you want to do. So you will be able, I mean, you decide the topic, then you implement a neural network to solve this problem, and then that's basically it. Okay? But what we expect for you to do is to implement one of those neural networks that we'll see in the second part of the course. Okay? So my mission for this year is that hopefully by the end of this course you will have a strong and comprehensive understanding of deep learning. You will basically learn how to design deep neural networks for various probabilistic inference tasks. And also you will be able to train this model, to train these neural networks. And so this is really important. This is something I really want to emphasize. This is not a course about how to use AI, but rather it's a course about how to build neural networks, okay, to solve tasks. So we'll not talk about how to write prompts or these kind of things. This is not the topic of this course. We'll rather see how you can actually build something close to ChatGPT if you want it. Okay? So the models that we will cover in this course, they have many applications, and I hope that you will get inspired to use them for anything that you want. They have applications, of course, to implement AI systems, but not only. They have many other applications in engineering or in science. All right? And you will see that by the end of this course, you will be able to do that. All right, so let's start. So deep learning, why learning? So to motivate this question, I will start with this slide and ask you a very simple question. What do you see? Fungi, mushrooms, yeah? How do you know that? Do you all see the mushrooms? Can you raise your hand? Okay. Who is a mushroom expert in the room? No one. Have you seen these ones before? Yeah, a few of them, but the majority of you have not. So how do you know that these images contain mushrooms? How do you do that? Yes?
I had a biology class about those, but I don't remember the names.
Okay. But many of you have not, and still they are capable of telling correctly that, yes, they are mushrooms. So, for example, where would be the mushrooms there? Is it there, or in the middle? In the middle, yes. Where would it be? Where would they be? I don't know, in these ones. Mostly everywhere, I suppose. Where would it be in this image? There is no mushroom, you say? Okay, I don't know. I think there is one there. Okay. But the important question is to ask you, how do you do that? How are you able to guess correctly that they are mushrooms? Okay, let's take another example. Do you see dogs in these images? So there are mops and dogs. Do you see a dog there? Who says yes, there is a dog in this image? Raise your hand. 2? Okay, it's a mop. In this one, is it a dog or a mop? A dog, correct. In this one, a dog? Okay, this one. Okay. Again, how do you do that? Okay, last example. There are chihuahuas in one of them and muffins. Is it a chihuahua or a muffin? Okay, and in this one? And in this one? Several of them. Okay. Okay, so the question is, how do we do that? We can just look at images and quickly understand the content, even when the content, like in the two previous examples, they visually look very similar. We are able to catch small details that make us understand that actually this is a muffin or this is a chihuahua. Okay? But the important question that you should ask yourself is if you want then to implement this in a computer, if you want to make a computer to see, you should be able to describe that so precisely that you can actually write a program which would be able to tell the difference between a chihuahua and a muffin. But would you be able to describe that so precisely that you can write this program? How do you do that? Okay, so this is a bit puzzling because for us, I mean, the human brain at least is so good at interpreting visual information that sometimes, and it's quite difficult to assess intuitively the difference between the representation of something and the actual thing. So, for example, if I show you this image, which is just a bunch of pixels, you can, I'm sure all of you tell me that, and very quickly tell me this is a mushroom, okay? But actually it's not a mushroom, it's the image of a mushroom. Okay? That's the same image. If I zoom in, okay, now you should start seeing the difference between the actual thing, the mushroom, and its representation. Now you notice certainly that, okay, there are these small squares that represent the pixels, okay, but your brain is still able to make sense of all these small squares together and to associate to this image the concept of mushroom. Okay? But actually your brain or your eyes do not directly see that. What do they see? Something more like this. Okay, the pixels, they are just a superposition of three colors, red, green, and blue. Okay? And you don't even realize that in these pixels, there is not just a pure color, it's the superposition of these three things. Okay? Your brain is doing that for you. But really, if you were to zoom in on the pixels, for example, of a screen, a computer screen, you would see eventually these three colors. But you don't even realize that. Okay? And for a computer, the actual representation of an image is something like this. Okay, just a bunch of numbers. It's a big table, a big array, where you have as many elements as pixels, and for each pixels you have three numbers, one for the three channels, red, green, and blue. Do you still see the mushroom in this slide? Well, it's the same content. Okay? So for a computer, a mushroom looks, I mean, the image of a mushroom is something like this. And now the big question we'll try to answer in this course is, okay, how can we write a computer program which would be able to make sense of this kind of data, where we do know that there is a mushroom. We don't know how we are able to do that, but yes, there is a mushroom in these numbers. And we'll have to, our goal will be to write a computer program which will be able to make sense of all of these numbers. So, how would you do that? How would you write a computer program that would be able to take an image and tell me, or tell, that yes, in this image there is a mushroom, there is a dog, there is a cat, there is something else? How would you do that? Anyone? Yes?
Analyzing shapes.
Okay.
Like the mushroom, it's round.
Yeah, so a mushroom, at least when we draw a mushroom, certainly we'll do something like this. So there is the ground, and then there is something like this, and then there is like that. Okay, that's the typical way we would represent a mushroom, even though mushrooms actually come in various forms. And if you want to write a computer program that is able to make sense of these images, it should be able to recognize all of these mushrooms. Okay? But supposedly, when we were small childs, when someone told you this is a mushroom, this is certainly something rather like this that you've been shown. Okay, and I'm sure you have never been taught that all of these images correspond to a mushroom. Yes?
We gather like millions of pictures of mushrooms,
Mm-hmm.
we feed them into an algorithm, we try to detect statistical regularities of what is a mushroom or not.
We feed that to an algorithm. What kind of algorithm? Okay, but let's continue maybe with the first approach, where we would have to detect the shapes. How would you do that? If you were to implement a program that has to detect shapes, what would be the next? So, for example, for the mushrooms, what kind of shapes would you try to detect? Like maybe this part? I mean, a shape like this, maybe, I don't know, like something like this, and maybe something like this. Okay? So you could try to specify a mushroom as a composition of basic shapes. There is a cap, there is a, what do you call that? I don't even know. But this part, and these two parts are connected to one another, so you should first detect the two of them and then see if they are connected at the right position. Okay? So that would work certainly for this species of mushroom to some extent, but it would be very difficult to certainly have a computer program which is as good as you are to detect the mushrooms. Okay? So we can do that for cats. Okay? And we can say that similarly a cat is made of several parts. It's made of a head, and it's made of a body, it's made of a tail. To the heads there are two ears that are attached. They are pointy, so you can just say they are triangles. Inside the head there are two eyes, there is a nose, and so you can be as sophisticated as you want, okay, and try to describe as precisely as possible the concept of a cat to a computer, okay? And it could work to some extent, but just like for the mushrooms, it certainly would be very, very difficult to account for all variations of a cat. Like in this image, there is a cat, okay? But if you were trying to show this very image to a computer program which thinks that a cat is something like this, then of course it wouldn't work as well. And so this approach is very limiting because you have as a programmer to basically anticipate for all these variations. Okay? And that becomes very, very complicated. So basically the conclusion is that to extract semantic information, we need models, computer programs, with a high complexity or with a complexity which is so high that it becomes very difficult, if not impossible, to describe this model manually. Oh, okay? So we'll abandon this strategy, and in terms of the research community, no one is doing that anymore. However, and that might be a bit surprising, is that you can write instead a computer program which is able to learn the task of extracting the relevant information itself. And to do that, we can indeed, for example, start from a data set of collection of images in which we know there is a cat, in which we know there is a dog, in which we know there is a muffin, okay? And then just train this model, adjust its parameters, such that eventually it makes correct predictions on these images. Okay, and this is what we call the machine learning approach. It's made of two simple steps. First, you define a parametric model. So basically a mathematical function with parameters, and this function is, for some configuration of the parameter, is able to produce correct, very good, or maybe bad predictions. In this course, of course, the kind of parametric model we'll consider are neural networks, but you've already seen other kind of models, for example, in Introduction to Machine Learning. You have seen, I don't know, linear models. This is one example, where you have two parameters to fit, the slope and the offset, but then you just fit these two parameters such that you do as best as you can on the data. Okay? But that's exactly the same recipe we'll follow. In deep learning, we'll define a parametric model, usually a very big neural networks with many, many parameters. And when I say many, many, I'm saying in 2025 in the order of several hundreds of millions or billions of parameters. And then we'll optimize the parameters of this model by basically making this model work on the training data, meaning we will adjust the parameters such that eventually it makes correct predictions for the data for which we know the truth. Okay? All right. So the machine learning recipe itself is not something new. That's something researchers have been working on, I don't know, since the 80s. However, what has changed is the kind of model we've been using and what we call the deep learning revolution. So deep learning itself is not that new anymore, but it basically it got to work eventually in I would say around 2012, where for the very first time people were able to show that yes, you can just train big neural networks and it will work. Before that time, it was very difficult for anyone to train this neural network. And there were several reasons for these obstacles. First, the hardware was not ready. So it's only when you scale this neural network to really bigger and bigger models that eventually they work very well. But to do that, you need machines, you need dedicated hardware, because they can be quite expensive to run. Second, you need very large data sets for them to understand the concept that you want them to learn. If you just have, I don't know, a few tens of images, then it's too few to understand the concept. You need in the millions, if not more. And also the algorithms themselves, they were not ready completely before that. So it's also because of discoveries in deep learning, in the algorithmic components, or in the way to train these algorithms that eventually we got them to work. Okay? But other than that, deep learning really is just the same recipe, the same machine learning recipe, but you scale everything up. Okay? So instead of having small models like linear models, you have larger and larger models that we call neural networks or deep neural networks. You train on even larger data sets and use even more computing resources to train them. Okay, so let me start then with this video from, do you know this guy? A few of you. So who is it? So this guy is named Yann LeCun. He got the Turing Award, so which is the Nobel Prize for computer science, for his research on and his contributions to deep neural networks, to deep learning. And he will tell you about his story, he has been working on this kind of models since the 80s, if not a bit before that. But it took very long, like 30, 40 years for them to eventually work. So he will tell you about the story and a bit about the present. So this video, I'm sorry, it's in French, but I think most of you understand, but I know maybe some of you do not. But that's the only video in French that I will show.
Il y a eu des hauts et des bas. Une certaine partie de la communauté, en fait, nous voyait comme des rêveurs pas très réalistes. Je suis Yann LeCun et je suis connu pour avoir grandement contribué à ce qu'on appelle le deep learning. Si vous retirez le deep learning de Facebook, Amazon, Google aujourd'hui, les compagnies s'écroulent. Le deep learning est une branche de l'intelligence artificielle utilisée dans tous les systèmes de reconnaissance d'image, reconnaissance de la parole, compréhension de texte aujourd'hui. Ce qui m'intéressait là-dedans à l'époque, c'était l'idée de s'inspirer un petit peu du type d'apprentissage qu'on peut observer chez les animaux et les humains. On ne sait pas écrire un programme directement qui permettrait à une machine de reconnaître un chat d'une voiture, d'une table, d'une chaise. Donc pour ça, il faut se reposer sur l'apprentissage et les réseaux de neurones artificiels, en particulier les réseaux convolutifs, qui sont un peu mon invention. Donc je vais vous raconter un petit peu comment ça s'est passé. Ça a pris une trentaine d'années. J'avais 20 ans, donc j'étais en 2e ou 3e année d'école d'ingénieur. Et j'avais jamais entendu parler de ça avant. J'ai trouvé ça fascinant. Et je me suis aperçu qu'il y avait eu beaucoup de publications entre les années 50 et la fin des années 60, et puis après, plus rien. Il y avait très peu de travaux sur le domaine dans l'informatique à l'époque. Je voulais vraiment faire de la recherche. Je ne savais pas comment m'y prendre, mais c'est vraiment ce qui me passionnait. Donc je commence mon doctorat en 83, et aux alentours de 83, justement, Terry Sonowski et Jeffrey Hinton publient un article qui passe inaperçu, mais qui pour moi était vraiment important, qui en fait lève la limitation qui avait conduit les chercheurs dans les années 60 à abandonner les réseaux de neurones artificiels. Ça s'appelle les réseaux de neurones artificiels parce qu'en fait ces systèmes sont des espèces de simulations numériques de réseaux de neurones qui sont interconnectés les unes avec les autres. Quand on construit un réseau de neurones, on connecte les neurones les uns avec les autres, et on peut avoir des réseaux de neurones qui ont une couche ou deux couches, ce qu'on faisait dans les années 60, ou plusieurs couches. Et la grosse question, c'est comment on entraîne un système qui a plusieurs couches. Et en fait, j'ai trouvé une méthode pour faire ça. Jeffrey Hinton, avec ses collègues, on a découvert une version un petit peu améliorée, donc on appelle la rétropropagation de gradient. Et c'est cette méthode-là, en fait, qui a fait démarrer le domaine des réseaux de neurones artificiels à la fin des années 80. Je pars au Canada, dans le laboratoire de Jeffrey Hinton, et là, je fais une autre trouvaille qu'on appelle, donc on a appelé les réseaux convolutifs par la suite. Je suis resté juste 1 an parce que j'ai été recruté par Bell Labs, qui se focalisait entièrement sur la recherche sur les réseaux de neurones artificiels. Il faut comprendre que Bell Labs, à l'époque, c'est un endroit mythique. C'est là qu'ont été inventés le transistor, le laser, les cellules solaires, les caméras CCD, le système Unix, le langage C et C++. Si on vous offre un job à Bell Labs, vous ne pouvez pas refuser. Donc j'y suis allé avec l'idée d'y rester 1 an ou 2 et puis de retourner en France. Et en fait, je suis aux États-Unis depuis 32 ans. Comme les gens se sont un petit peu désintéressés des réseaux de neurones au milieu des années 90, j'ai un peu changé de sujet. Je me suis intéressé à la compression d'images, des choses comme ça. Puis ensuite, je deviens professeur à l'Université de New York. Et là, je redémarre un programme de recherche intense dans le domaine de l'apprentissage automatique. Donc là, je me réunis avec Yoshua Bengio et Jeffrey Hinton, et on démarre une espèce de complot pour essayer de raviver l'intérêt de la communauté pour ces méthodes de réseau de neurones. Une certaine partie de la communauté, en fait, nous voyait comme des drivers pas très réalistes. On fait un rebranding un petit peu, on renomme le domaine des réseaux de neurones Deep Learning, apprentissage profond. Mon ami Jeffrey Hinton, en 2012, a gagné une compétition qui s'appelait la compétition ImageNet. Il a utilisé un grand réseau de neurones entraîné avec un peu plus d'1 million d'images, à classifier des images dans environ 1000 catégories différentes. L'amélioration des performances par rapport aux méthodes plus classiques était telle que la communauté de la vision par ordinateur s'est dit on ne pourra jamais rattraper ça avec les méthodes classiques. Donc ça a conduit à une espèce de révolution dans laquelle les gens du jour au lendemain en fait ont complètement changé leur méthode préférée. Et ça a beaucoup attiré l'attention de l'industrie. À partir de ce moment-là, des compagnies comme Google, Facebook, un peu plus tard Amazon, Baidu, etc. commencent à se dire on va vraiment pouvoir appliquer ça. Et donc elles se sont jetées dessus. Après la victoire d'ImageNet, après les progrès en reconnaissance de la parole, etc., il y a eu une explosion. C'est devenu une énorme communauté avec une industrie derrière, avec des postes de recherche dans le monde académique, dans la recherche publique. Et ce qui m'intéresse, effectivement, c'est le mystère de l'intelligence d'une manière générale, pas seulement l'intelligence des machines, et donc le mystère de l'apprentissage. On a encore beaucoup de progrès à faire, on est encore très très loin, en fait, de pouvoir reproduire les mécanismes d'apprentissage et certainement d'intelligence qu'on observe chez les animaux et les humains. Les machines les plus intelligentes aujourd'hui ont moins de bon sens qu'un chat gouttière. Il y a eu des hauts et des bas.
Comments? So this video is a few years old, much before ChatGPT. So his opinion is more or less still the same, but it's a bit more nuanced now because now we have much better system than what we thought at the time. Okay, but basically that's about it for the story of deep learning. And so what's the state of deep learning today? So I will describe that in 2 steps. The first step is that basically with deep learning you can build what I would call specialized neural network that you can train to achieve performance which is better than human performance or on almost anything, even if these tasks are complex. And so this is something that previously we thought was out of reach for the machines, but today it's very common to have systems, for example, that are able to make sense of images. So this is the case of what we call a segmentation network, in which the goal of the task is to segment, so to isolate a bunch of pixels and to associate them all together in a concept. So for example, all these pixels, they correspond to a car. These other pixels in blue, they correspond also to a car, but a different car. It's another instance. These pixels at the front, they correspond to a person, and so on and so forth. Okay? You also have other tasks, plenty of other tasks in vision. This is what we call human pose estimation, where the goal is first to detect the persons and then to detect the pose, so the kind of virtual skeleton of the person, like the head, the body, the arms, and so on. This is the problem of estimating depth, so estimating 3D from 2D. So if I show you these pixels that you see in blue, would you say that they are far or close from the observer? They are far. Okay, they correspond to sky, and the sky is very far from the observer, from the camera which took this image. But this is something quite, which is very easy for us, but that can be quite complicated for systems. But also that's something that you can frame as a machine learning problem, where you start from an image and then you just want to predict as output another image which corresponds to the depth that you have, for example, that you associate to each pixel. You can also have systems that play games, video games, or board games. So this is the example of AlphaGo, which is able to be the very best players in the world, even though the game is very complicated and the number of possible ways to play the game is gigantic. This is something that now machines are able to do, and to do much better than anyone on Earth. You can also have systems that take images and describe the content of these images, or vice versa. You also have systems that can take a piece of text, and then you are able to ask questions, and they are able to answer. Okay, so this is something many researchers from the community have been working on since the 2012, I would say, and since then, the state of the art has consistently been replaced by deep learning solutions, and now everything is driven by deep neural networks. But then you might ask yourself, okay, what's the point of having thousands of researchers trying to classify pixels to detect cars? Do we really need that? Or similarly, what's the point of trying to detect these persons and the heads of these persons? Why do we spend so much money on this problem? So what you should understand is that actually this is just a pretext, okay? And what you should understand is that these neural networks, they form some kind of primitives that if you are able to solve this problem, then you can transfer these primitives to many other domains. So conceptually, if you understand that, and if you manage to train a neural network to classify pixels to detect cars, well, certainly you can transfer the same neural network or the same architecture, and you just retrain this neural network. For example, so all these examples are transfers to the medical domain, in which, for example, in this image, we use the same kind of segmentation network, but not to detect cars, to detect tissues, to detect cells, to detect malignant cells, and so on and so forth. But conceptually, it's just the same kind of neural network, and even mathematically, the task is defined exactly in the same way. The only thing that changes is the data that you use to train this neural network. The same, for example, here, if you want to detect melanome, I don't know the word in English, and you want to classify them from serious to, okay, you should really not care about them. That's also something that you can frame as a classification problem, and you can use the same kind of neural network to solve this task. Okay, so there are plenty of examples like this. So this is the example of medicine, but you have the same kind of applications, for example, in the domain of energy, where many of the tasks that we would need, for example, in the energy sector or towards clean energy can also be framed as machine learning problem. And in this case, you can call neural networks to help you solve this problem. So I will not show you this video. You can watch them later. This is another video from Google, which is just showcasing a few applications of neural networks in medicine. And finally, this one is the example of an autonomous car by Waymo, in which they also tell you how they decompose the problem of having a self-driving car navigate the environment by just decomposing that into smaller tasks like detecting obstacles, detecting other cars. All these tasks can be solved independently by small neural networks, and then you recompose everything into a virtual environment, and then you make decisions. Okay? So you can go very, very far by just using these neural networks, and you can use them already now, and for some years actually, to solve many, many, many things. However, in parallel to these improvements on this specialized task, a breakthrough happened, I would say, in 2017 with a paper called Attention is All You Need, which proposed an architecture which we call the transformer architecture, which initially was used to develop a system able to do translation, where you have a piece of text in one language like French, and you want the neural network to produce the same text but in another target language like English or Dutch or something else. Okay, so they proposed this architecture. It worked very, very well, much better than anything that happened before. But what we also noticed is that this same architecture can be used to do many, many other things. So you can use this architecture to generate data, to generate text. You can use also this same architecture to process images by transforming an image into a sequence of small parts, small patches, and many other things. And so what we quickly realized and quickly noticed is that this architecture works very well for almost anything. And so the state of the art basically today is just to use variations of this architecture, of the transformer architectures, for almost everything that you want. And what is a bit more interesting and actually mysterious about this architecture is that it's very simple, and it's able to ingest so much. So by that I mean, if you just instantiate one of these transformers, the more data you train on, the better the results. This is not the case for the other kind of neural networks usually, where eventually you will see a saturation. The capacity of the neural network will be saturated. In the case of the transformer, of course, there is eventually a saturation, but it's much more, overall, the capacity is much bigger. Second, the more parameters you have, so simply the larger this neural network, the better. So, okay, if you have a system and the performance that you get is not very good, you can just make your neural network bigger, and you're almost guaranteed that you will get better results. And finally, the more compute, so the longer you train, also the better the model. Okay, so this is not very smart, I agree. But this is a very successful recipe. Just use more data, more parameters, more compute, and you will get success. And usually you will get results that beat the state of the art. Okay? And what is, at least at the time, so this figure is already a couple of years old, but at the time we were not seeing also any sign of slowing down. We were not seeing this saturation that we think will reach eventually. So you see in these plots there is no sign of saturation. The more compute you have, you see that it's decreasing. The larger the data set, you see it's decreasing. And the more parameter, it's also decreasing. Okay, and you don't see any sign of saturation. Okay, so with these transformers, I suppose many of you actually have already, if not all of you, have already used them. Maybe you don't realize that, but that's the kind of model which is behind ChatGPT and other chatbots. So this is the case, for example, of Claude from Anthropic. So any conversational AI assistant or AI agent is using a transformer behind. So I will not show you this video. I suppose you all know about these systems. What you may maybe not know is that well, I suppose you also know that, but many of these AI assistants are also more and more present in applications you would use for other things. So, for example, you have AI assistants now in code editors. You have also that in Word or other systems that you would use. It seems that everyone wants to put this system everywhere for some reason. We can debate about whether or not this is good or bad, but this is an example where you have someone, so this girl, she's 8 years old, and because she's using one of these AI assistants, she's able to, within just half an hour, to develop a website where she's able to talk to Harry Potter, and this website is hosted in the cloud. Are you able to do that? She is. And so maybe you can quickly watch a part of this video. Where is it?
Hello, everyone, and today, I'm going to show you how to code with cursor. I'm gonna get a terminal.
The cursor is a code editor which is AI enabled. It's really the core feature.
npm run dev. There. I hit that. And then I go to B. And look, I made it say hello. I want this to say.
And then she's just using the chat to ask the editor to write the corresponding code.
Hello. And then if I do that, then it will basically have some code and it will apply it. I'm going to do Command Tab and Command R. And now, look, now it says Harry Potter. So now I'm going to say put Harry Potter in the middle of the screen. There. Now it's going to replace this. Present. Okay, use the center. Harry Potter. Now it's going to do this, which I'm going to apply, which adds it to it and changes the code that needs to be done. And then refresh. Look, it's in the middle. And that's a really good font. Add a text box. Now we have this. Apply it, accept it. Look. Expect.
Okay, so you get the idea, so you can watch the entire video if you want. But what this is showing you is that the systems, they are really enabling people that may not have the technical skills, but with these tools they are able to do things, to build stuff. Certainly she's not understanding anything about the code, okay, but is that really relevant? I don't know. At the end of the day, she's able to get the website that she wanted. Okay, so this is really a revolution in my opinion, and what's really a revolution is not really what's below, okay? This is just a transformer, and this has been known since the 2017. What's new really is the interface, okay? What happened with ChatGPT is that eventually everyone could use them, okay, by just talking to this system, by just asking questions, and you don't have to be a technical expert, you don't have to know what's a neural network to just talk to these things, okay? So what's really new is the interface. Okay, so you can have this system, of course, to generate text, to understand text, and have this kind of code assistance and other things. What's also happening is that the system, they are becoming more and more multimodal. So by that I mean that they are able to understand not only text, but also images, speech, and many other things into a single model. And that's quite new. Actually, this is quite challenging from a technical point of view, and also in terms of deep learning that you need to do that. But that's something that is happening. And to show you that, we'll show you a last demo, this one of ChatGPT, where this is the video version, which you have, for example, on your smartphone if you have the ChatGPT application. So you can talk to it, but also you can activate your webcam, your camera, and it will also understand the video feed from the camera. And so in this case, they will ask the system to play a game, rock, paper, scissors, and the system will be able to understand and actually play the game with them.
Hey, I'm Alex.
And I'm Miana.
Hi, Alex and Miana. Nice to meet you both. How's it going?
It's pretty good. We're trying to figure out what should we play. Do you have any suggestions?
Absolutely. How about a classic game of rock, paper, scissors? It's quick, fun, and you don't need any...
Great. Can you count us in and sound like a sportscaster?
And welcome, ladies and gentlemen, to the ultimate showdown of the century. In this corner, we have the dynamic duo, Alex and Miana, ready to throw down in a...
Okay, just count us in.
All right, here we go. In 3, 2, 1, shoot. Now, show your hands. What did you pick?
Who won?
Would you look at that? It's a tie. Wow.
Okay, let's
That
do
was
it again.
close. Round 2, here we go. Get ready. And 3, 2, 1, shoot. Let's see those hands.
Who won?
And it's another tie.
Okay,
Use
let's
your-
do it again.
All right, third time's a charm. Here we go. 3, 2, 1, shoot. Let's see those picks.
Who won?
And we have a winner. Miana's scissors cut through Alex's paper. Great game, you two.
Pretty cool. Thank you.
Thanks.
Okay, so I think this example is very interesting because let's just think about what you would need to do if you were to try to implement that game yourself in the usual classical way. How would you do that? That would be quite a challenge. But the system, okay, it has never been programmed explicitly to play that game. It has never been told explicitly the rules of the game. It has never been told that these two players were Alex and Miana. It has never been told that Alex was the guy to the left, and the other player, Miana, was to the right. It has never been told the concept of a hand, which you need. It has never been told that this is a paper, this is scissors, this is rocks, even though they may come also in many, many variations. It has never been told that this hand is attached to myself, one of the two players. It has never been told that, okay, when you have two symbols of the same categories, then it's a tie. It has never been told that the scissors will win over the paper. Okay, so I mean, if we were trying to implement that 10 years ago, I don't think we would have managed. Okay, but now you have systems that are able to do that almost out of the box. Okay, because they understand so much. They understand text. They've been trained on the entire human knowledge. They know everything, and they are now also able to understand videos and speech, and to unify that into a same model. Okay, so I think the applications and the benefits of the systems are still yet to come. This is still in the infancy. They are still in their infancy, I would say, and this is just more like a proof of concept for now, but I think in a few years from now, we'll have many applications, many of these systems a bit everywhere, and there are certainly many benefits that will come with these applications. However, where is the mouse? I think as engineers and computer scientists, you should also realize that to reap these benefits, we should be aware also of the many risks that comes with this system. And so I would say that with great powers comes great responsibility. You can use also, of course, the system to do many, many bad things if you wanted. And so this is a serious concern that we have as a research community. So very recently, a couple of weeks ago, actually, this report was released, the International AI Safety Report, which is the result of a collaboration by more than 100 researchers in the field, in which they identify various risks that are becoming more and more real, I would say, as the systems are getting better. And basically, this report classifies risk related to general purpose AI systems into 3 categories. The first one is simply the risk that may happen because of malicious use. So of course you can use this system, you can imagine that you can use this system for scam, to manipulate people, or to design weapons, like biological or chemical weapons. If you want to know how to build a bomb, you can just ask one of these systems and they will tell you. Maybe not all of them, because they have safeguards. Like if you try to ask that to ChatGPT, for example, it will say, okay, I cannot talk about that. Okay, but there are plenty of other open source LLM, for example, where you don't have these safeguards. Second, there is also the risk of malfunctions. So I'm quite sure you are quite familiar with the concept of hallucinations, which is the fact that many of these systems, where they don't know, they don't know, they don't know. And so they will just keep babbling and very confidently tell you about things that are actually quite wrong. So they will completely hallucinate, as we say. But if you are not an expert or familiar enough with the topic of the conversation, I would say, then you may not realize that this is completely wrong. Okay. There are also biases. So all these systems, they come with values, and usually the values of their designers or owners. And so these values, they may not align with our own values. So if you ask ChatGPT, I don't know, about the events at Tiananmen in China, you will get some answer. If you ask the same thing to DeepSeek, you will get quite a different answer. Okay? So there is a bias, and you should realize that. There is also a loss of control that may come with these systems. And finally, there are also systemic risk. And so this is also a concern. So many jobs are at risk of changing. So many of these systems are able to do tasks that were or are currently giving purpose and meaning to many people. So if you ask a secretary, she or he does things that now can be almost automatically replaced by these systems. So many of these jobs, maybe including mine, certainly, and maybe yours, will change. And so this is something that we have to know and understand and account for. There is also a big divide in the research community. So there is a risk of having the research community to divide into mostly by countries or continents. It used to be, and I hope it will remain like this for a few years, if not more, that we were a big community globally and we were all working together. But more and more, many of this research is done secretly at companies. So what OpenAI is doing, we don't know really. What Microsoft is doing, we don't know really. What Google is doing, we don't know really. What other players in other continents are doing, we don't know really. And finally, there is also risk of power concentration. So if everybody is using ChatGPT then, and becomes almost dependent on the system, then companies like OpenAI or other things are basically concentrating a lot of power, and we should also realize that. Okay, so if you are interested by these questions, I really invite you to have a look at this report. There is, okay, we don't see it, but there is a link just there. It's a long report of 200 or 300 pages, but it's also there are executive summaries if you just want the quick story, and they have many interesting points. One of them, which is also a growing concern, is the environmental impact of AI. And what they say in this report is that, for now at least, AI is a moderate but rapidly growing contributor to global environmental impacts. Of course, because of the energy they require, okay, and also because of the greenhouse gas emissions that they produce. However, currently in 2025, the current estimate indicate that data centers and data transmissions account for more or less 1% of global energy-related greenhouse gas emissions. And within this 1%, AI is consuming between 10 to 28% of the energy. Okay? So basically, it means that AI, for now, at least in 2025, is consuming a third of 1% of the global energy that we all consume as humans, which is not that much, okay, relatively, okay. However, what may be a concern is that the demand of energy for the system is growing, and is growing exponentially, okay. So it may not take very long for this third of a percent to become much, much larger, okay. What you should realize is that in the energy consumption of data centers, you have also everything related to other things that require data centers, like YouTube, Netflix, and everything like this, which consume much more than AI systems. Okay, and then finally, before we go back to the technical details, that's a slide that I've decided to add. We should all realize that as the more we are using the system, the dumber we all become. I will really say it like this. And that's something we are starting to be able to actually quantify. So this is a paper which was released a few weeks ago by researchers from Microsoft Cambridge in the UK. And basically, their conclusion, or one of the main messages, is this one. So when people rely on generative AI, like chatbots, ChatGPT, Claude, and others, their efforts shift towards verifying that an AI's response is good enough to use. Okay, just ask a question, it will tell you a very nice thing, and just say, okay, does it look good or bad? That's it. Instead of using your higher order critical thinking skills, like creating, evaluating, analyzing information. And if humans only intervene when AI responses are insufficient, okay, which will become certainly less and less frequent as the systems get better and better, but that will still happen nonetheless. So if humans only intervene when AI responses are insufficient, then workers are deprived of routine opportunities to practice their judgment and strengthen their cognitive musculature, leaving them atrophied and unprepared. So basically, and that's something we can measure, the more you use the system, and if you delegate too much to the system, you should realize that you are becoming less and less skilled, okay? You are becoming dumber, okay? And unfortunately, I really want to insist on that. That's something I'm starting to also realize with you, the students. There used to be, I mean, like 5 years ago, it was not like this, but now I've very often students that, okay, they just put the instructions of projects to the system, they get some initial answers, and then it's just adjust a few things and that's it, but you are missing an opportunity to learn and to practice the skills that are really important. Okay? Anyway, that's just something I wanted to say. Okay, but to end maybe on a more positive note, where I think deep learning is really shining is that it can also solve problems that no one could solve before. And this is where I think you have the very best applications of AI, is to solve things that no human could solve before, okay? So there are also many, many examples. I will quickly flash a few of them. The first one is AlphaFold. So AlphaFold is a neural network which actually got the Nobel, for which the authors got the Nobel Prize of Chemistry a couple of months ago. And the goal of this neural network is to predict the 3D structure of a protein. So as you may know or may not know, a protein is a sequence of amino acids, like a long string of amino acids. But in the real world, this long string of amino acids will take a shape, okay, a 3D shape. It will stabilize into a shape, like the one that you see rotating. And why is it important to determine or to understand the shape of a protein? Because it's the shape of a protein which gives it function. If you understand the shape, you understand what it does. Okay? But for very long, the way we could try to determine the shape of a protein, of a sequence of amino acids, was by doing very expensive and long experiments in a wet lab, or doing various or using various and expensive instruments. And that worked, but this is very slow. Okay, and there are many proteins that will not be able to analyze in the lab in this way because the space of proteins is just so large that we can't just analyze them all. And for very long, this problem was really an open problem in the field. Many researchers have been trying to determine in silico, so with a computer, the 3D shape of a protein, but the performance was not very good. And in 2017, and then later on in the second version in 2021, then eventually we got performance, which again was much better than anything before. And now the accuracy of the system is so good that we can actually use them to do science. We can use them to biology or biochemistry and all these things. Because we are confident enough that the shapes that are predicted by the systems are very close to the actual shape that we have in reality. Okay, so this is really a game changer for a field. It is completely changing the way biology research is working, and through that there are many other important applications like drug discovery. If you understand the shape of proteins, then you can also use that to discover new drugs and so on and so forth. You can watch this video if you're interested. It's the story about the breakthrough of AlphaFold. This is a second example, which is also a bit related, which is the problem of trying to discover new drugs. Again, with neural networks in this case, and graph neural networks more precisely. So I don't know if you ever wondered how do we actually find drugs to treat diseases. Usually it's by chance. Many of them have been discovered by chance. And if not by chance, then you have someone very smart who thinks for very long and basically filter out a few interesting molecules or promising molecules, and then we do experiments in a lab to see if these molecules, where, for example, if you want to, let's say, discover new antibiotics, you put bacteria together with a molecule, and you see if they die or not after some time. Okay, so just trial and error usually. And the issue with this is that if you want to discover new drugs, meaning if you want to discover new molecules that would have an effect, then we have to explore a space which is very large, which is the space of all possible molecules. Okay, and for example, if you consider the space of molecules that could have a pharmacological effect, then you have in the order of 10 to the 60 possible molecules that you would have to test. That's big. Okay, so there is no way we can just try them all. And so what has been done in this paper is to use a neural network to basically filter out at least some promising molecules that then have been tested in the lab. And you can use, in this case, so what they propose to use was a neural network, a graph neural network to solve this task. And actually, in this paper, they have discovered a new antibiotic with a neural network. A last example is the case of weather forecasts. And so what you see there is a neural network called GraphCast, which is used to do accurate weather forecast. So, okay, there you could argue that actually weather forecast is something that we've known how to do while using a neural network. What you should, however, realize is that the physical model, the numerical model, they are good, but far from perfect, and they are also very slow. So every 6 hours or so, the European Center for Weather Forecast, for example, is releasing new forecasts for the next 2 weeks into the futures. This is refreshed every 6 hours, but these forecasts, they require a lot of compute. You need entire data centers to produce this forecast. So this is very expensive. And also it's somehow accurate, but not that accurate. There are plenty of things that are not accounted for in these numerical models. And so with GraphCast, Google shown to everyone that actually you could use a very big neural network also to challenge the very best numerical model. And so in this paper, they achieved for the first time performance accuracy, which was comparable to classical numerical predictions. And now there are even better systems. So the next generation is actually now reaching performance which is better than numerical models. So it's better, and of course it's also faster, because now to make these predictions, you just need to make a few forward passes through your neural networks. That will take, for the biggest one, in the order of minutes, which you have to compare to several hours inside a big data center for the classical approach. All right. So before we start, I want to conclude this first part of this introduction by this quote from Chris Bishop, but really that's the philosophy that you should have when it comes to AI and deep learning. So for the last 40 years, and that's something I did myself as a student, and I suppose you have done also yourself, we've been taught and we have programmed computers. Okay, the philosophy I think you should now switch to is that instead of programming explicitly everything, what we'll be doing into the future now, and certainly for a long time to go, is we'll just train them to do what we want. Okay? And the only thing that you will have to program are the neural networks and everything around them for this to work. Do you have questions? Remarks? Okay, so let's do a break and we'll resume at 10 for the first lecture.